Okay, one more question. I am Dr. Ben Newman, and this is Ask Dr. Ben, where I try to use my experience as a coronavirus researcher to answer your questions with papers. Yeah, that's what we do as scientists. This question is a good one. This is a banger, yeah, from Amy. So, it's talking about a particular paper which is linked down at the bottom. It's a bioarchived preprint. So the question is, I know it's only in vitro, still it makes me wonder if we need to rethink the use of convalescent plasma or use it more selectively and cautiously, and the risks associated with that. So what's the paper? Well, let me click on my other tab so I can actually tell you the title of the paper. So it's SARS coronavirus 2 escape in vitro from a highly neutralizing COVID-19 convalescent plasma. What does that mean? It means they took antibodies that one person made in response to having the virus. And they put those into, in this case, not a second person. That is a thing that we do. And it does work reasonably well if you do it right. But they put them into just like let's imagine a petri dish. You would not use an open top petri dish to grow a virus this dangerous. Yeah, I don't know. Your safety person would want to have a word, I would think. And so you put the antibodies in there, and these are all pre-made antibodies, so they can't change after this point. They're only exactly what this person made way back when. And you put the virus in there, and then you just allow the virus to grow a little bit. You put the antibodies in maybe at a low amount, let the virus get going a little bit, or you do it a bunch of different times. And what they found is that over time, the virus actually changes, and it will change in a way that will avoid those antibodies. Now, we tend to think of a virus like a little person or like a little pet, like it has some intention and it's moving in a direction. They don't work like that. Viruses make mistakes at random all the time, just all the time. And then what happens is that out of all these different versions of the virus, all the ones that can be killed by an antibody will disappear. And so those will all be gone. And so you'll only have, the ones left that couldn't be killed by an antibody. And those will then be able to merrily go out and infect all the other cells. So the virus growing will make all the different variants, and the antibody will select so that you end up with just the variants that the antibody couldn't kill. And so you can say, oh no, the virus has evolved, and this is a thing that is actually reasonably easy to do in the lab. And that's exactly what this study is. Coronaviruses, given the opportunity, given the reasonable chance, will make whatever mutations they have to make, because they make those mutations anyway. But you can select, a particular mutation, and you will end up with a virus that is at least somewhat resistant to whatever it was you used to do the selection. Yeah, that's how every virus works. Now, why isn't this an enormous problem, or is it an enormous problem? It's not a huge problem, I would say, but it's something to watch. Yeah. So the reason it's not an enormous problem is that, one, in an active immune response, so you've got not just the antibodies that you made last week or last month, you also have some of the cells that made those antibodies, and so you can make new ones. And so there are different ways where you can refold an antibody or add something onto an antibody. There are ways that your body ends up taking things it's already made, and it's like with leftovers. They sort of freshen them up, and you get an antibody that is then able to bind something a little bit different. So it's able to have a little extra life. And also with cells, you can keep pumping those out. And with an active immune system, if you see another virus, if another virus comes along and you get a little bit of exposure to that, you can start to make an immune response against that, and you can make another very specific immune response. So not such a big deal. The other reason why I don't tend to worry about this as much is that when viruses change, most of the time they change, think of it this way, they change because they have to, not because they want to. As if a virus could want anything. So the virus changes because you're pushing it in a direction with a drug, with a treatment, with an antibody. And it's not changing just because that makes it a better virus, because chances are, with no selection, what you will get out will be something that's pretty close to the best virus that that virus can be. You'll get something pretty near the top of the pile, because that's the one that'll spread better, that'll transmit better, that'll grow better, that'll do everything. It's just everything better. Yeah. So generally, the virus you catch is already pretty close to optimum, and when the virus changes in response to whatever you're doing to it, instead of being at the top of this thing, you pick a virus that's changed. It's somewhere down here. It's going to be less fit, less good at some feature of whatever makes a virus good at doing its thing. Pretty much any change you make in a virus makes it worse. People have done this experimentally for many different viruses. This seems to be generally true. And it's the same idea behind why radiation, which causes random mutations, usually doesn't produce Spider-Man powers in people. It usually produces cancer in people. Yeah, which I call the Spider-Man paradox. And you can have that for free. Go ahead. Go use it. Yeah. Random mutation is almost always bad and almost always catastrophically bad. Yeah. No, I wouldn't say rarely. I would say almost never. Yeah. Do you get Spider-Man powers? Do you get any kind of added effect? So, back to the actual question, which is here. So, what does this mean for how we use convalescent plasma? Is it a thing that we need to ration or like only use in certain cases, like an antibiotic would be, I think, the point of comparison? I would say probably not. So the reasons here, and again, I'm giving you a lot of reasons, but these are things where we don't have a study where somebody's just done it and I can say, yes, here, done. It's always, we don't know for sure, but here's why I think this. That's, yeah, closest I can get to a real answer. So we know that convalescent plasma works, but only when you give it fairly early in the outbreak, like when a person just catches the virus and has still very mild symptoms. Doesn't seem to do much for people that already are hospitalized or on a ventilator or have really severe symptoms. And it doesn't seem to do much in terms of stopping those people from dying, which is really what you would want it to do. So it's a thing that only works on the mild cases. And yes, potentially, you could end up selecting for versions of the virus that are resistant to a particular person's antibodies. So the thing is, you take the antibodies out of all different people, and so you're never going to give the same antibodies to two different people in the same balance. Everybody makes their own version of an anti-SARS-CoV-2 antibody, and this convalescent serum is a mix of all kinds of different antibodies. Which bind to different parts of the protein, and you're just not going to get the same thing from any two people. So, yeah, it can be resistant to this one thing, but it's not going to be resistant to other people's antibodies or even your own. So, in general, I think the best thing is make your own darn antibodies, get vaccinated, and then you've got the cells, like the factories to make antibodies, as well as the products, which are the antibodies themselves. And you can just retool the factory in various ways to produce slightly different antibodies to kind of play catch up if the virus strain changes enough that becomes necessary. And then, even then, if there's somebody that needs convalescent plasma therapy, I think it is just fine. I mean, that's a decision their doctor would make, but I don't think there's a good scientific reason to say, don't do this or reserve it only for the very sick, because probably it doesn't work for the very sick. You will get the most effect on people that were probably going to be okay anyway, and it can potentially prevent somebody from getting really sick if that's what was going to happen. But once they're already there, it's pretty hard to stop. So yeah, good question. Lot to unpack there. I hope I did an okay job of unpacking it. If there's something that I said that was not very clear, and there's probably something there, please send in another question and I'll try and pick up that aspect of it. But I hope that helped anyway. Thanks very much. This has been Ask Dr. Ben.